let's do some actual physics problems. So review question 1. We have a model airplane that heads due east at 1.5 meters per second, while the wind blows due north at 0.7 meters per second. The scale diagram below, scaled, this is to scale, represents these vector quantities. So you can download this from the description, and we have this to scale, which means that if we measure how many centimeters this is, we can come up with a scale for the length of each vector and what 1 centimeter is equal to. So the first question says, using a ruler, determine the scale. Now, we could do this for either vector, but I'm going to choose this one right here. And if we measure this, this comes out to, let's see, 4.5 centimeters. So we have 4.5 centimeters is equal to 0.7 meters per second. So if we divide through both sides by 4.5, so we say 0.7 divided by 4.5, that gives us 0.156. So we have 1 centimeter on this side is equal to 0.156 meters per second. And that should make sense. For 4.5 centimeters, if we multiply that by 4.5, we're going to get our 0.7. So we found the scale. 2. On the diagram in your answer booklet, use a protractor and ruler to construct a vector diagram. So we've done this before, but we were freehanding it before. Now we have to do it to scale. So we have to be a little bit more careful. So we want to draw a rectangle, but a rectangle means that we have to have right angles. So we're going to take our protractor, place this here, and line that up there. And this way, we can make sure that we have a truly right angle. Do these a little closer. And then to complete our rectangle, we need another vector. Now you can see I've got a problem here because the diagram's not long enough. So what I'm going to do is I'm going to extend this line down. So that now, when I put this on the tip of the arrow, and I have something to line this up with over here, so I make sure that that is actually at 90 degrees. And now, I can draw in my vector. Actually, it's just the dotted line, not the vector yet. And this point right here is where we know is the tip of the arrow. So we could do the tip to tail method and move that up. Or we just realize that from tip to tail, it must be starting here at the two tails and ending up here. So I'm going to do that over again. Okay, so we completed the diagram. Determine the magnitude of the resultant velocity. Well, we have a couple of different ways we could do this. We could do Pythagorean theorem to get it, or we could use the scale that we have. So if we go ahead and look at this, we have 10 centimeters to here, and we have an additional 0.9 centimeters from there. So the length of this is 10.9 centimeters. And if we multiply 10.9 centimeters times our scale, which is times 0.156 meters per second per centimeter, then we get 10.9 times 0.156, and that gives us 1.7. So this is 1.7 meters per second. And then lastly, determine the angle between north and the resultant velocity. And we have a couple of choices. We could use tangent of theta, because we know this side is 0.7 meters per second. Or we could just use our protractor. And since we have the protractor out, we can say that that is 26 degrees, 26 or 27. I'm looking at this from an angle, so it's not perfect for my perspective. And that's 26 degrees. Question number 2. We have a motorboat which is traveling at 5 meters per second east across a river. So our first vector is 5 meters per second east, and our second vector south at 3.3 meters per second is going to be down like that. So our resultant vector in the tip to tail method is going to be from here down to here, which is nice because this forms a right triangle. And when we have two sides of a right triangle, we can use Pythagorean theorem to find the other. So we have a squared plus b squared equals c squared. Put our numbers in and solve for r. R is 5.99, which is close enough to be 6 meters per second. This problem's great because it's the opposite of the problem we just did. In this one, we have the resultant force of 24 newtons acting at 35 degrees above the horizontal. So that's horizontal to the resultant. And it's asking for the magnitudes of the horizontal and vertical components. In other words, we're looking for f of h and f of v. So they already drew in our dotted lines for us. So we already have our right triangle. Let's solve for f of h first. So this is our adjacent side and our hypotenuse. So we're going to use cosine. Cos theta is equal to adjacent over hypotenuse. So that's cos 35 equals adjacent FH over 24 newtons. So we have cos 35 times, cos 35 times 24, and that's going to be 19.66 newtons. And then for the f of v, we're going to solve for this side because that's the equal side of the rectangle. So that's going to be sine theta equals opposite over hypotenuse. So that's sine 35 equals opposite f of v over hypotenuse 24 newtons. So we're going to do sine 35 times 24 when we cross multiply, and that's going to give us an FV of 13.77 newtons. And we can look at our choices here. 19.66 is going to be pretty close to 20, and 13.77 is going to be pretty close to 14. And we can see here we've got 20 and 14 for FV. Which diagram represents a box in equilibrium? So equilibrium means the sum of all the forces equals 0. The vector sum of all of these vectors has to balance out to 0. Well, these two would cancel each other, but we'd be left over with some force here. These two forces would cancel, but these would not. We'd be left over with 3 newtons of force. Here we have 5 newtons and 5 newtons canceling each other, 2 canceling 2. So that gives us a net force of 0. This one's a little bit tricky. So it says in the diagram below, a 20 newton force due north and a 20 newton force due east act concurrently. Now, that word concurrently just means with the same time. So two forces acting on each other at the same time. on an object as shown in the diagram below. So we have these two forces acting on this box, and what's the additional force necessary to bring the object into a state of equilibrium? So we need the force that's going to cancel out these two vectors, but these vectors are only the components. We need to find the resultant. So this isn't too bad. That's our resultant there. So we can do a squared plus b squared equals c squared. So we have 20 newtons squared plus 20 newtons squared equals our resultant squared. So we have 20x squared plus 20x squared equals 800 second square root second, I hit the wrong one, second square root of 800 gives us a resultant of 28.3, and that's going to be in newtons. But this is the tricky part on this. This is the resultant of 28.3 newtons, but it's asking for what is producing this in equilibrium. In other words, what's going to cancel out this force? Well, that's going to be a force of 28.3 newtons this way. So if this is northeast, we need a vector that's going to be 28.3 newtons southwest. So approximately 28.3 is about 28, and that's 28 newtons to the southwest. Okay, as the angle between two concurrent forces, two forces at the same time, decreases, what happens to the magnitude of the force required to produce equilibrium? So let's take a look at a couple of forces here. Let's say we have some forces like this, at a very large angle from each other. We know that in the parallelogram method, we could move that vector over here, roughly, and that would be our resultant vector. But what would happen as the angle gets smaller between these two vectors? Well, now, if we use the parallelogram method and move this vector over to here, we can see that the vector length gets larger. So as the angle between forces decreases, the magnitude of the force produced equilibrium increases. Number 7. A force of 60 newtons is applied to a rope to pull a sled across a horizontal surface at a constant velocity. The rope is at 30 degrees above the horizontal. Calculate the magnitude of the component of the 60 Newton force that is parallel to the horizontal surface. So really, all they're asking us in this question is, what's the component parallel to the surface? Well, if we put our rectangular box around this, we can see that what they're asking us for is this. So let's call that force horizontal, and we'll say that this is 30 degrees, and this force is 60 newtons. So we're back to having a sine, cosine, tangent problem. We have the adjacent side, and we have the hypotenuse. So that's going to be cos theta equals adjacent over hypotenuse. So we're going to have cos 30 equals adjacent, f of h, over a hypotenuse of 60 newtons. And if you remember from before, cos of 30 is 0.866, and multiplying that by 60, that gives us a horizontal force of 51.96. I think we can round that up to 52 newtons. In this one, we have to draw the resultant vector. So they're already set up in the tip-to-tail method. So all we have to do is go from the tail up to the tip. And that is our resultant vector. So if you want to look at this a different way, you can see that the vectors, that this vector right here, if we slid that down, would be right here, and the position at which they would cross would be here. So the components are going to produce a resultant vector that's going to split not quite in the middle, closer to the side that's longer. And that value is equal to this value. This one's a little bit tricky because we have been given one component and one resultant, and we're looking for the other component. So if we take our first component and add it in here like this, then we have to figure out what the component would be that over here that would make our resultant be here. Well, we know from the parallelogram method that we end up needing something that's going to be equal to this. That's this idea here, which is that vector right there. So what vector choice in here is going to be equal to something in that range? It's going to be vector B. Number 10. Determine the length of both vectors in centimeters. So to do that, we're going to use our ruler. There's 10 centimeters, and that's about 1.5. So this is 11.5 centimeters. And finding the length of this vector is about 6.3 centimeters. Okay. Determine the angle between both vectors. So if you put this down like this happens a lot. We're not quite lined up with that. So we're going to extend this arrow out. So that we can figure out the exact value of that angle. And that's going to be counting this way, 10, 20, 30, all the way up 110. And that's going to be about 118 degrees. Use a ruler and a protractor to draw the resultant. So now we're at the tricky part. So we want to take this vector and slide it over here. But this vector has to maintain the same angle. So this angle in here is going to be our crucial angle. So we could use our protractor, but we could also just say that 180 minus 118 is the angle. So that's 62 degrees in here. So over here, we can line this up and go to 62 degrees. So we have 60 right here. 62 is going to be about there. And I'm going to draw this as a dotted line because we don't know the magnitude of this vector. So it's 6.3 centimeters. So we know that this side also has to be 6.3 centimeters. And we can complete our parallelogram like that. And now all we have to do is draw our resultant vector, which is going to be from the two tails up here. And that's going to be our resultant vector. Measure the length of the resultant in centimeters. So we have, that is basically 10 centimeters. Might be a little tiny bit more. if 1 centimeter equals 5 newtons, what's the magnitude of the force? Well, if 1 centimeter is 5 newtons and we have 10 centimeters, then the resultant is going to be 50 newtons.